Hi folks, I have created a playlist which deals with the modeling of axisymmetry or axisymmetric parts in the 3D Experience release 2022 for fun and environment purposes. Now, I was under the impression that actually this was not implemented, but I was told by the people at the SAW that this came about in the release 2021, which is last year. So now at least you can do axisymmetric analysis, and in the near future, it may be plane strain and plane stress parts. The purpose of the tutorial is to show the people who are new to 3D Experience, or they're transitioning from the Abacus CAE program to the 3D Experience, on how things are different, how things can be done in the new interface, and in what sense it may be different from what they see in the Abacus program. All the icons and the interface, everything has changed, okay? So this is to introduce them to the new interface, basically. Keep in mind that the FEA solver in the 3D Experience is in fact the Abacus program. So I got some information from Mr. Martin at Dassault System that the axisymmetric modeling has been implemented or migrated to the release 2021x of the 3D Experience, and there is a very nice video that he has prepared, but this is an unlisted video, and therefore I'm unable to give you the link to it. However, I'm trying to compensate that by doing the present video. There will be other ones that will follow suit. So the particular problem that I'm going to do is by this YouTuber, and he has done this problem using the Abacus CAE in a step-by-step fashion. So I'm going to replicate his steps, and this way you can see what the differences are as far as the interface and icons. The problem is a thin-walled spherical pressure vessel, which is under internal pressure. Now this can be modeled with axisymmetric shells, or it can be modeled with the axisymmetric continuum, 2D continuum problems, and that's how it is done, okay? It is not using the axisymmetric shells, but instead axisymmetric continuum element, 2D continuum elements. So the dimensions are given here and material properties are there. So this is a classical problem in strength of material, and the well-known result is that the radial stress through the thickness of the spherical or through the shell is 0, and the hoop stress and the meridional stress are the same, and it's PR over T. P is the internal pressure, or is the radius, nominal radius of the sphere, and T is the thickness, okay? So the mesh that we're going to use is roughly this size. This is all from that gentleman's work in the Abacus CAE, so I'm going to use that. And we're going to activate the nonlinear geometric effect, and these are the initial increment and the maximum increment and the minimum increment that this fellow is using. Okay, so I will quickly take you through some of these slides, but we'll come to it when we need it. We'll come back to this later on. The key feature is that you make the model, 3D model, and then you have to go to the model assembly design in order to do the rest of the problem. And notice that when you do this, you have the option of choosing axisymmetric axisymmetric icon. Okay, so I'm gonna stop this, but we'll come back to that later. Okay, so let's go ahead and make this. So on a convenient plane, on that vertical plane, I will sketch. But we're going to be using the quarter quarter of the model. When I say quarter, it's actually 1/8 of the spherical shell. So let me go ahead and make two 90-degree arcs, one like that. Okay, so this is going to be 21 inches, 21 millimeter. This dimension is going to be 21 millimeter. Okay, we make another one which is 19 millimeters, and that's the inside of the tank. Okay, so let's give a dimension. This is 19. So the 19, the nominal radius is, as you can see, 20, and the thickness is 1. The thick, something's not working out here. Wait a minute, so this is 19. Okay. So here's what I mean. If you look at it, the nominal radius is 20, the outside circle radius 21, and the inside radius is, actually this should be, the thickness is 1, so 20.5 and 19.5. This is not correct. So let's go ahead and fix this thing. This is 20.5. All right, and this is 19.5. Okay, so notice that the thickness of this thing is 1. All right, let's close this. So from here to here, and from here to here. Okay, exit, and using the essential feature, we shaft this thing about the z-axis by 360 degrees. Okay, so what you see there is actually the top face of the top portion of the tank. Now, what I need to do, this is very important, I need to create a point which eventually is going to be used as the origin of the coordinate system, and it must be in a geometrical set. So notice that I have to go to the geometrical set. I'll call it my set, okay, and I create a point with coordinate 0, 0, 0 in it. So this point is in the geometrical set. If you try to do the same problem with this point being outside of that set, it's not going to work. That's the way they wrote the program. Okay? I will also create a coordinate system which is centered at this location. Here is the axis system right there. This axis system, you click on it, automatically creates a coordinate system at that location. Notice that if you turn this thing around, you see the point and you see the coordinate system that's that's sitting there. We don't necessarily need an axis system. It can be any line, but if you're making a line, for example, 2 points in the geometrical set and a line in the geometrical set, they almost reside there. But if you do an axis system is always outside of that. Okay, that's good. That's pretty much it. Let's apply material to this thing. So go to tools, create a material. Let me go there one more time. Create a material. Let's call it Axisymmetric. Okay. Right there. Apply. I'm going to close that, apply to that part, and now we go and input our parameters on numbers. Double click on this. Okay, structural. We don't need the density, so we need the abacus multiphysics, mechanical, elasticity, elastic, and 200,000 MPa, and Poisson ratio of 0.3. These are standard properties for steel. Okay, we're pretty good. We're in good shape. Now, ordinarily, one would go to structural model creation, okay, and then create the mesh. But this is an axisymmetric feature, which code has been written for it. So you don't go there. You go to model assembly design. Model assembly design. I put this thing in my favorite apps because in order to do the axisymmetric problem, I need this guy. So it's in my apps, but I put it in the favorite apps. So I'll go to model assembly design. Okay. I think, yeah, this, and already we can see that we are there. You can see that. Let me see for a second. Yeah, so already I am there. So see, I'm already in there. So if I, for example, go to, just hypothetically, if I go to this again, it will open up a new window. You see that? Another tab, but that's the reason this happened is because I'm already there. So I'm going to close this. I don't need it. I'm going to save it right there. So here is what I had in mind. Once again, make sure that you are the top level branch of the tree before getting to model assembly design app. And I was already there, so I don't have to worry about that. Okay, see? Good. So we click on this guy, automated FEM. Click on automated FEM, and here is your axisymmetric feature here. Click on it. Okay. So what I'm showing you there, you can either create a 2D continuum from these. See, these are 2D continuum, or you can do what is it called? Mesh, the axisymmetric shell. You can do the continuum one, or based on beams, you can create axisymmetric shell. I don't want to do this in this tutorial. I'm just using this. So look at what it's asking. It's asking for the plane. So I have to choose a plane, which basically tells you where that axisymmetric profile is going to be. So I can use YZ or XZ, or I could have created another plane, doesn't matter. I will use YZ. It says, where is the origin? The origin is that point that you created and you put in a geometrical set. If this was outside the geometrical set, you would not be able to pick it. So, and it says, what is the axis? The axis, I created that coordinate system because I can use its Z axis. If you don't do that, you have to create a line there and then pick it. Okay? And then it says, don't forget this. It says, what is the geometry? The geometry is this body. And as soon as I did this, notice that it made those beam elements disappear. Okay? Now the size, let's start with the mesh size. I don't know, I'll make it 4. You may have to make it bigger or smaller if it's not, reasonably comparable to this, although we don't have to, but anyway, so let's see. Okay. Now if you zoom in, you see that that element size was too big. So let's go back there. Let's go back there. Instead of 4, let's make it, I don't know, actually, let's make it, mesh size is 4. So this length is 1. Remember, this length is 1. Let me also go to edit parameters, because here you can specify the number, the mesh size, and let me see the growth. This is fine. Let's make this thing 1 actually. Let's make it 1. Oh, see, this is better. However, we want something else. So let's make it a 0.4 or 0.5. Let's see how it looks like. Yeah. We can even make it smaller, 0.25. This is much finer than what we had there. So we say OK. And OK. All right, so there's my mesh. This is much finer than what that YouTube link is doing. But this is fine. But notice what happened here. We have two, as soon as we did this stuff, two abstraction shapes were created. Okay, so basically they have written the code so that when you do this, this is a two-dimensional axisymmetric cross-section, and notice that this changed to R and Z. These two are created. Okay. So where are we with the slides? So we are right here. If it doesn't show you the mesh, just update. It'll show it to you, but we're good. Okay, so let's move on. And in the tree, the point must be in that geometrical set. We already know what this thing is. These are the two abstraction shapes that were created. Okay, we'll worry about this later on. There is some online documentation, and I just took 2 pages out of it. You can check that yourself. Okay, so now we're going to go to structural scenario creation. This is where you apply the load and restraints and things like that. So we're going to choose the finite element mesh, finite element model. Okay. So first thing we're going to do is procedure. We're going to do static step. And remember, we're going to make this thing 0.1. Let me see what this thing was. Even these large numbers is going to work, but I'll try to stick to what is done in this fellow's work. 0.1, a maximum 1, and this is 1 e to the minus 10. I really don't need that thing, so I'll just leave it like this. We see how it goes. And geometric nonlinearity is on. Okay, I don't think you need that such a small minimum increment number. Okay, good. So let's go to restraints. So this bottom cannot move in the direction Z. So we click on it, cannot move in the direction Z. Notice that all the stuff that we did, it converted the stuff to the RZ coordinate system, which is used for axisymmetric models. And then this other edge does not move in the R direction. Okay, and under the load we have pressure of 100 MPa. Let's see for a second. 100 MPa. Good. Go on 100 MPa. All right, so let's go ahead and run it. I think we took care of all the stuff that we needed. So first of all, a model check. And then simulation check. And once this is finished, we're going to go and run it. It's almost finished. Yep. And now we simply simulate. I will create another tutorial when you use axisymmetric shells, okay? That's different from what we're doing now. We're not using shell elements. Here we're using continuum elements in the axisymmetric plane. It's almost done. Very good. Close it. First of all, this is the initial increment. Obviously, this is a 0, but let's look at the displacement, for example. So everything is 0. When you go to the next step, of course, it's going to move out. And all the way at the end of applying 100 megapascal, this is going to be the deflection. Okay. If we look at the stresses, on these stresses, again, circular pattern as you see. And now we also want to do a couple of things. We want to check the hoop stress and the the other two stresses, hoop stresses. Those are principal stresses. So in order to do that, we have to go and ask for them because it doesn't give it to us by default. So let's go back to the standard tab, click on the scenario, and then click on output and select all the stresses. We just want the principal ones, but let me see, are the principal stress? Yeah, stress components, good. That's all. That's really all we need when I checked everything. Yeah. And we say OK. And we're going to run it again. If you don't want this, you can, but you can hide that. Yeah. Yeah. It's going. So if you check the principal stresses, they better be 1,000. And of course, the radial stress, one of them is the radial stress, or one of the principal stresses is going to be 0. So let's close this. Let's see, do we get it here? We don't get it here, but that's okay. We can click on go to plots. You can click on contour plots. And for stress components right there, we can select the principal ones. So let's say, let's try let's say maximum principal. That should be 1,000. Apply. Yeah, pretty much almost 1,000. And if you look at the minimum, it's going to be 0. So we go to minimum principal. That's the radial stress. Apply. Which one is this? Oh, this is mid, not mid, minimum. Well, minimum. Minimum principal. For all practical purposes, 0. Okay. So this is a problem that we did. It's fairly reasonable. The things that you have to watch for is this is a very valuable resource. This is the example that we're doing. Notice that you have to go to the model assembly design application, and in order to get there, you just make sure you're at the top level assembly. select the specialized axisymmetric, okay, and your automated FEM. There are three things that you have to select. There is the plane, vertical plane of axisymmetry, origin that you created in the geometrical set, and the axis that either you have it as line in the geometrical set or a coordinate system that I did. And if you can't see the mesh, just update it. As soon as you do these things, if you have a object there, solid object there, that's the only thing that you can do. But if you have a surface, then you can use the cylindrical shell that I'm going to do later on. Yeah. Oh, something I forgot to do. You can go there and you can show actually something very nice. So let me close this. If you go to display, and you click on results option, you can actually show this thing in a 3D view. So for a second. So you say sweep axis symmetry and 0 to 90, for example, or 0 to, I don't know, 180 if you want. It's entirely up to you. Let me try 180. And how many segments? Let's make it, 20 segments. Notice what happens. It shows it to you as a fake three-dimensional variation. Okay, it's really, this is already done in the axisymmetric plane, except that you can make it show it to you in 3D. Yeah, I'm glad I didn't forget to tell you this.